Okay, so now what we're going to consider is the angular momentum of a system of particles. So a bunch of particles interacting with each other. And what we're going to discover is that angular momentum, just like energy and linear momentum, are strictly conserved quantities. Okay, so if you have a system that's isolated, then whatever angular momentum it had to begin with, no matter how the particles interact with each other, you will have exactly the same angular momentum at the end of that interaction. Okay, so another thing to say here is that by particle, we mean a point particle. And this is important because as opposed to an extended rigid body like this. And that's because remember that when we're going to be talking about changes in angular momentum, which are caused by torques. And a torque depends critically not just on the force, but the point of application of the force. So if I apply this force at this point on this rigid body, it will exert a counterclockwise torque about this axis. Okay, if I apply the same force at a different point in the body, say down here, it will exert a clockwise torque about this axis, a totally different torque depending upon the point of application. And when I'm applying the force, say at that point, I'm really applying it to that point particle right there, which is connected to other point particles in that body, and so that particle will exert, internal forces on neighboring particles, and they will exert internal forces on particles neighboring to them, and so on and so forth. And the force will be transmitted through the body. Okay, similarly down here, when I apply a force at that point, it's really being applied to that point particle, which then gets transmitted to other particles in the rigid body through internal forces. Okay, so we need to be careful when we're doing physics to really be clear about what we're talking about. Okay, so what we're going to consider is the simplest possible system of particles. Okay, that's 3 particles. So we can have 2 in our system and 1 external. Okay, to illustrate the main point here. All right, so we've got, say, a point particle, which we'll call point particle number 1, located over here. And we have a point particle, which we'll call particle number 2, located over here. And we'll have a third point particle down here. And instead of calling it point particle number 3, we'll call it the external point particle. Okay, so that represents particles external to what will be our system. Okay. Now, these particles, of course, they will exert forces on each other. And those forces will be in Newton's third law action and reaction pairs. So suppose that these 2 particles are positively charged, and so they will exert electrostatic forces on each other. Okay, so particle number 2 will exert a force on particle number 1. Let's call that F12. And likewise, particle number 1 will exert a force on particle number 2, exactly equal magnitude, opposite direction, F21, like that. So that's a Newton's third law action and reaction pair. And now suppose that this external force, just for variety, exerts gravitational forces on particles 1 and 2 in our system. Okay, so the external particle will exert a gravitational force on particle number 1, which we'll call F1 external. And of course, if the external particle exerts a force on particle number 1, then particle number 1 exerts a force on the external particle of exactly the same magnitude, but opposite direction, so we put a minus sign in front. Similarly, the external particle exerts a gravitational force on particle number 2, so that's F2 external. And then particle number 2 will likewise exert a gravitational force on the external particle, which is exactly the same vector, but opposite sign. Okay, so we have 3 Newton's third law action and reaction pairs of forces. And those forces acting on these individual particles, the net force acting on each individual particle will change the linear momentum of that particle. So these 2 particles are, say, doing this kind of motion because they're electrostatically repelling each other. And suppose that the momentum of particle number 1 at this instant of time is, say, P1. Okay, so it's moving in that direction. And of course, the net force is going to be changing that momentum, and the trajectory will bend like that because the force is generally in that direction. And similarly, let's suppose that particle number 2 at this instant of time has some linear momentum P2, okay, in that direction. And of course, this external particle has some momentum, and under the action of those forces, that momentum will change. But we know that linear momentum is a strictly conserved quantity. It doesn't matter what these interaction forces are. If this is an isolated system, then the change in the linear momentum of the system will be always 0. Okay, whatever the linear momentum was to begin with, regardless of what interactions happen, the linear momentum after those interactions will be exactly the same. Okay, so linear momentum is a is a conserved quantity. Now, angular momentum is also a conserved quantity, strictly conserved in exactly the same way. But now this is a little bit slightly more complicated because what causes changes in linear momentum are net forces. What causes changes in angular momentum are net torques. Okay, so whenever we talk about angular momentum or torque, we need to specify about which point are we evaluating that angular momentum and about which point are we evaluating those torques. Okay, so that point is completely arbitrary. We can choose it to be anything we want. Let's choose it to be this point over here. And we assume that we're in some inertial reference frame, and we will choose the origin of our inertial reference frame to be right at that point O. So here's our inertial reference frame, and here's our special point about which we will be evaluating all torques and angular momenta. Okay? Now, in order to evaluate torques or angular momentum, torque is R cross F, angular momentum is R cross P. Okay, and so we need to identify, well, what is the location of particle number 1 relative to O? Well, that's the position vector R1. And what is the location of particle number 2 relative to our special point O? Well, that's the vector R2. Okay, so I think we have pretty much everything on here. Okay, so next what we're going to do is we're going to take these three particles, 1, 2, and external, and we're going to put a big box around them, and we're going to call that the total set of particles. Okay, and so this is the total. And we will assume that this total is isolated. Okay, so isolated with regards to, in this case, angular momentum. So we have no angular momentum entering our set of three particles and no angular momentum leaving. Okay, and that happens, what changes angular momentum is torques. So we can either imagine there's nothing out here, no other particles exerting any forces and thus torques, or we can even imagine there are particles outside of this, but the net torque that they exert on all the particles in our system is 0. So either way, the system is isolated, no angular momentum in, no angular momentum out, which means that the total angular momentum doesn't change. So no angular momentum in or out, which tells us that delta L total, the total angular momentum, never changes. Okay, so whatever the angular momentum was to begin with, whatever these interactions are, the system, the set of all these three particles will have exactly the same angular momentum for all time. Okay, so the total angular momentum remains constant. Okay, now what we're going to do is we're going to say, okay, that's great for this system for this set of three particles. Now we want to pick from those set of three particles a subset of particles. And let's take it particle 1 and particle 2. That we're going to call our system. Okay, so particles 1 and 2 will be our system. And that system in general will be not isolated. Okay, so you can see that our system of particles 1 and 2 is not isolated because it's interacting with a particle external to the system. So there can be exchanges of angular momentum between our system of particles and the external. Okay, so the angular momentum of the external particle might change by, say, this amount. Then the angular momentum of our system of particles must change by that amount, so that the change in the total angular momentum remains is 0. Total angular momentum remains the same. So we have delta L total. Well, the total angular momentum of all three particles has two parts. So there's a angular momentum associated with the system of particles 1 and 2, and there's an angular momentum associated with the external particle or particles. Okay, and the idea is, well, delta L total is equal to 0. So it tells us that, sure, the angular momentum in this system of particles that interact with external could be changing. And what's that change? Well, that change is the negative of the change in the angular momentum of the particles external to the system. So if the if the particles external to the system, like I said, have a change of angular momentum in that direction, angular momentum is a vector. If there's a change in angular momentum in that direction, then there must be a corresponding change in angular momentum of the system in that direction so that the total angular momentum doesn't change. So in that case, there will be angular momentum transferred across the boundary, okay, from this particle to these particles, okay, and vice versa, the negative the other way. Okay, and so, just like you have, a force acting over time transfers linear momentum, a twisting force or a torque acting over time transfers angular momentum. It's exactly the same stuff. Okay, you'll see exact parallels with what we talked about before with linear momentum, now with angular momentum. Okay, and we should also identify internal and external forces. Okay, so there are a bunch of forces here, and so the forces that are internal to our system, well, those are the F12 and F21. Okay, the forces that the particles within our system exert on each other. Okay, so there's F12 and there's F21. And we will assume that those internal forces satisfy Newton's third law, action-reaction. We're going to have to be a little bit more strict on this. Okay, you'll see it's a little bit more subtle than just this. Okay, and then there are external forces. So by external forces, of course, we mean the forces that the external particle exerts on the particles internal to our system. So that's F1 and F2 external. So F1 external and F2 external. Okay, very good. Okay, so so now what we want to do is say, well, okay, we're wondering this system of particles at this instant of time has some angular momentum about that point O. There will be an R1 cross P1, there will be an R2 cross P2, that'll be some vector, there'll be some angular momentum about the point O. So the system angular momentum at this instant of time in this picture, so L system, the angular momentum in the system of our two particles, is going to be the angular momentum of particle number 1 about point O plus the angular momentum of particle number 2 about point O. So it's really important. These angular momenta are being evaluated about this fixed point O in this inertial reference frame. Okay? And now that angular momentum of our system, because our system is not isolated, it's interacting with an external particle, that angular momentum in that system could be changing. Okay? And so let's work it out. So what is the time rate of change of the angular momentum in our system of two particles? Well, it's just the time derivative of the angular momentum in that particle number 1 has about the origin, plus the time derivative of the angular momentum that particle number 2 has about that origin point. Okay? And then we remember, so what causes changes in linear momentum is net force. What causes changes in angular momentum is net torque. Okay, and so the change in the angular momentum of particle number 1 is going to equal the net torque. So the sum of all of the torques acting on particle number 1, plus the change in the angular momentum of particle number 2 about that fixed point O is going to be the net torque that all of the forces acting on particle number 2 exert about that point O. Okay? And again, I'll just reiterate, these torques are being evaluated about the fixed point O. Now, it doesn't matter what point we choose, but as soon as we choose one, we have to stick to it throughout the entire analysis. Okay? Okay, great. So what are these things? What are the torques? Well, the torques are going to be the sum of the torques that are acting on particle number 1 about that point is going to be an R1 cross F12. That's an internal torque, plus R1 cross F1 external. Okay, and then plus the sum of the torques exerted on particle number 2 about that fixed point O. Okay, so that's going to be R2. Torque is R cross F. So it's R2 cross the internal force acting on particle number 2 plus R2 cross the external force acting on particle number 2. Okay, so we've got that. Now, we're going to group these into two terms. So these two that involve F12 and F21, those are internal torques. And so it's a sum of internal torques. So that's equal to the sum of torques that are internal to our system, that one particle exerts on the other and so on, plus the sum of the torques that the external forces exert. That's the ones involving F1 and F2 external. So that's the torques external to the system. Okay? Now, what we're going to show is that the sum of the torques internal to the system is, under most conditions, 0. Okay? So let's actually show that first. So this one is very important. Okay, so let's expand this. And so what we've got is it's the internal torques. So there's an R1 cross F12 plus R2 cross F21. Okay, so that's an R1 cross F12 plus R2 cross F21. But if we assume that F21 is negative F12, then this is negative R2 cross F12. Okay, we've just taken F21 and written it as negative F12. And so you can see that F12 is common to both, and so this is R1 minus R2 vector cross product with F12, assuming that the forces are satisfying Newton's third law, action and reaction pairs of forces. Okay? So, great. So what we're going to do is we are going to look at the conditions under which this is equal to 0. Okay, so when is that equal to 0? Well, it's equal to 0 in all cases that we're going to look at in Phys 121. But we want to be a little bit careful here and see why that's the case, okay? Because, you know, as physics majors, you want to understand stuff a little bit, where stuff comes from. Okay, so let's look at an example of contact forces. Okay, so contact forces between objects. And perhaps one of the simplest examples is something like this. So we have two disks. Okay, and so one disk is initially at rest, and the other disk is spinning counterclockwise, looking down from the top. And then we put those two disks in contact with each other. Maybe they exert gravitational forces on each other and they pull each other together. Okay, and so what's going to happen is the top disk is going to be spinning like this, and it's going to exert a counterclockwise, looking down from the top, a counterclockwise torque, a frictional torque. These surfaces are sliding next to each other. There is a mu k, there's a force of kinetic friction. Okay, so the top spinning disk will exert a counterclockwise torque on the bottom non-spinning disk, causing it to start spinning faster and faster, so transferring angular momentum in that direction to the bottom object. And at the same time, the bottom object is going to be exerting a twisting force or a torque on the upper object in the opposite direction, slowing it down. So its angular momentum used to be large in this direction, and so it's going to be decreasing. Okay, so the angular momentum transfer to the top object is down, and the angular momentum transfer to the bottom object is up, and so the total momentum, the total angular momentum of that system of two disks doesn't change. Okay, so let's look at that a little bit more carefully, thinking in terms of point particles. Okay, so we'll just pick a pair of points. So the two disks are in contact in a disk area, and we'll pick one point particle in the upper disk and one point particle in the lower disk, and they will interact with each other. Okay, so we'll draw the picture. It looks like this. So we have the top disk is like this, and that top disk is initially spinning counterclockwise, looking from below. So its angular momentum, its angular velocity is in the counterclockwise direction. So it's up. The angular velocity vector, omega 1, this is disk number 1. The angular velocity of disk number 1 is up like this. And then we put that disk in contact with disk number 2. Both disk number 1 and disk number 2 are rigid bodies made up of a whole bunch of point particles. Okay, So now we're going to focus our attention on, so let's see here. So let's take this point as the point between the two disks where they're in contact, the center. Okay, that's the center point between the two disks. And let's go outwards a little bit, radially outwards a little bit, to a point not at the center of those two disks, but a little bit outwards. Maybe not out towards the edge, but just some random point inside between the two. Okay, so this would be right to the very edge. And so now we take a particle in the upper disk, a point particle in the upper disk, okay, which is right there, and a point particle in the lower disk, which is right over there. Okay? Now these 2 point particles, they are interacting with each other. This particle down here in disk number 2 starts at rest, and the particle in disk number 1 is sliding past it like this. Okay? And so the particle that's sliding past that particle at rest is going to exert a force. So there's going to be a force on particle number 2, that's that particle over there, due to particle number 1 in that direction. Okay? And so there's going to be a torque. So that particle in disk number 1 is exerting a torque on disk number 2. Well, what is the torque? The torque is r cross F21. And so this vector is, it's a vector which we're going to evaluate the torques about that point O. Okay, and so the vector R1, which points from O to the location of particle number 1, is equal to the vector R2, which points from O to particle number 2, because these are point particles and they're right next to each other. And so the R1 is equal to R2. They're pointed to the same point because these are point particles. They're infinitely close together. Okay, and so the torque that particle number 1 exerts on particle number 2 is going to be R2 cross F21. So R2 is in that direction, F21 is in that direction, so that torque is up. So this vector here, this is the torque exerted on disk number 2 due to disk number 1, or the particle number 2 in disk number 2 due to the particle number 1 in disk number 1. Okay, and so what that is doing is we've got a spinning disk that's set down on top of a non-spinning disk. So that spinning disk, but through frictional torques, these are frictional forces. F12 and F21 are frictional forces. So that frictional force is going to exert a, looking down from the top, a counterclockwise torque on that bottom disk and make that bottom disk start spinning faster and faster and faster. So in other words, it's transferring angular momentum to that bottom disk. And that the rate of transfer of the angular momentum is the torque, tau 21. So the angular momentum that's being transferred is in the upward direction, which makes sense. This has zero angular momentum to begin with. As time goes on, it starts spinning faster and faster and faster and getting a larger and larger component of angular momentum in the upwards direction, the direction of the torque that's being applied to it. Okay, and likewise, particle number 2 is going to exert a force on particle number 1. This is a frictional force. This is force on 1 due to number 2, okay, which is in the opposite direction. These are Newton's third law action-reaction pairs of forces, frictional in this case. Okay, and so then that force on particle number 1 applied at that point represents a torque exerted on disk number 1. And what's that torque? Well, it's going to be R1 cross F12. So R1 is in that direction, F12 is in that direction, so the torque is down. So there's a torque acting on disk number 1 due to disk number 2, or due to the particle number 2 in disk number 2. Okay, and you can see that that torque is downwards, and so that's so the change, so the rate of change of the angular momentum of disk number 1 is torque 1, 2, and so the rate of change of the angular momentum of disk number 1 is down. And that makes sense because disk number 1 was initially spinning with an angular momentum omega 1 up. And so it had an angular velocity omega 1 up, so it had an angular momentum which was in the upwards direction. Okay, but the torque that's being applied to it is in the downwards direction. So it's taking a large angular momentum and making it smaller, smaller, smaller. And so the change in the angular momentum of disk number 1 is in the downwards direction, which is the direction of the torque that disk number 2, or particle number 2 in disk 2, applies to disk number 1, torque 1, 2. Okay, so anyways, but the basic idea here is, well, look, R12 equals R21. So this is equal to 0. And so the net internal torque, this guy exerts a torque on this guy in that direction, and this guy exerts a torque on this guy in that direction, and those torques add up. Torque 1, 2 plus torque 2, 1, those are vectors in opposite directions of equal magnitude, and so they cancel out. Okay, and then you can repeat that argument for all of the point particles, because you've got like two surfaces in contact with each other. We were just looking at one pair of point particles here, between like that point particle in the upper disk and that point particle in the lower disk. Okay, but now you can look at all of the point particles in the where those two disks are in contact. Okay, and so you can apply the same analysis to all of the points, and you will come up with the same analysis. R1 is equal to R2, and so, of course, the sum of the internal torques is equal to 0. Okay, so that's a really common and important example. There's lots of examples like this in Phys 121. So if this is the case, that tells us that the sum of the internal torques is equal to 0. Okay, in that case, contact forces. Now, there's another example here. There are also field forces. And now there are two sort of classifications of field forces here. So we'll talk first about central field forces. Okay, and so what does that mean? So that means field forces that act between particles, like here and here, like the electrostatic field. So the electrostatic field, by central we mean that the electrostatic force between two charged particles is parallel to the line joining those two particles. Okay, and so they are along the center line joining those two particles. And similarly, these gravitational forces, they point towards each other's center. Okay, and so they are centrally directed field forces. Okay. And so in this case, we'd have something like this. So here's particle number 1, here's particle number 2. So particle number 2 exerts a field force on particle number 1. Maybe it's electrostatic, maybe it's gravitational, but the point is it lies along, it's parallel to the line joining the two particles. So this is force on 1 due to 2. Okay, so that's that guy. And then there's a field force, say electrostatic or whatever, on 2 due to 1. Okay, it looks like that. And let's evaluate the torque that these forces exert, internal torques that these forces exert on those particles. What do you mean internal torque? Well, relative to some point. That point over there, let's say. So that point here, that's our point O. And so torque is R cross F, and so we need an R1 pointing to particle number 1, and we need an R2 pointing to particle number 2. And, and the net torque is going to be R1 cross F12 plus R2 cross F21. Now these two forces satisfy F12 equals minus F21, so the sum of those two torques is this. Okay, but now we look at this, R1 minus R2 is, unlike for contact forces, R1 minus R2 is not 0. Okay, so what is R1 minus R2? Like they're separated in space. They're not like contact, touching each other. Okay, so they're separated in space. So what is R1 minus R2? Well, it's that vector. So this is R1 minus R2. And you'll notice that if we have centrally directed field forces, so they point towards each other's centers or away from each other's centers, but they're parallel to the line connecting the centers of the two particles, then R1, the vector R1 minus R2 is parallel to F12. Okay, and so that immediately tells us, oh, the sum of the torques, the internal torques, is equal to 0. Okay, because the cross product of two parallel vectors is 0. Okay, and so that's true for central field forces, and that's what these are sort of the two examples that we'll consider in Physics 121. But there is another really interesting example, which I'll just sort of point out here, because certainly not all field forces are central field forces. Okay, so we'll consider non-central field forces as a counterexample, just to see that this is not quite trivial. So non-central field forces. Okay, so a nice example of that, the simplest possible example of that is this. Okay, so we have a positively charged particle like this, which is moving. We'll call this particle number 1, and it's moving at this instant of time with a velocity v1 to the right. And we have particle number 2, which is also positively charged, and it is at this instant of time moving with a velocity v2 in the upwards direction like this. Okay, great. Now Now remember, so I don't know if you know the Lorentz force law. So the idea is that electric and magnetic fields can exert forces on charged particles. And here certainly there are electrostatic forces. We'll ignore those for a minute. We'll focus on the magnetic forces. And so the magnetic field created by particle number 2 can exert a force on particle number 1. And the magnetic field created by particle number 1 can exert a force on particle number 2. So remember that if you have an electric current flowing through a wire, then it will produce a magnetic field that circles around the wire. So you put your thumb in the direction of the electric current and your fingers curl in the direction of the magnetic field. Okay, so particle number 2 is moving in that direction. That's like an electric current moving in that direction. So you stick your thumb in the direction of the current flow, the velocity of the positively charged particle, and your fingers will curl around, and that indicates the direction of the magnetic field. So if we evaluate the magnetic field here, it has come out of the board and then back in like this, and so it's coming out of the board at this point towards me. Okay, so to indicate a field coming directly out of the board, you draw a dot and a circle around it. So this is the magnetic field at that point produced by particle number 2 in motion. Okay, so that's B2. And similarly, particle number 1 is moving to the right. It's like an electric current flowing to the right. Stick your thumb in the direction of the electric current. Your fingers curl in the direction of the magnetic field produced by that flow of electric charge. Okay, and so that comes out here and goes into the board. So into the board over there. Okay, and so the magnetic field. So to indicate a vector going into the board, you draw an X with a circle around it. And so this represents the magnetic field at this and in the location of particle number 2 due to particle number 1. Okay? And then you might know that the force that a charged particle moving with some velocity in a magnetic field experiences is V cross B. The cross product is super important to master. Okay, so the force that particle 1 experiences moving at velocity v1 in field b2 is v1 vector cross product with b2, so that's a vector down. So this guy experiences a force. So this is the force on particle number 1 due to particle number 2, and it's equal to or proportional to, there's a 1 over c or whatever, depending on your choice of units, v1 cross b2. Okay. And now let's evaluate the force that experienced by particle number 2 moving upwards like this in a field that goes into the board, magnetic field that goes into the board. Well, you go V cross B is this way. Okay, so it's this way. So this is the force on particle number 2 due to particle number 1, the field produced by particle number 1, and that's V2 cross B1. Okay, so the first thing you recognize is that the force on particle number 1 due to particle number 2 is down. The force on particle number 2 due to particle number 2 is to the left. So it definitely does not satisfy this relationship. Okay, so here's an example where F12, just a super simple example, where F12 does not equal negative F21. And so Newton's third law, action-reaction pairs of forces, that idea fails. Okay, but conservation of angular momentum does not fail. Okay, conservation of angular momentum is always true. But here you have to consider the angular momentum associated with the masses in motion, the particles, plus the angular momentum associated with the fields. Okay, so under the action of these forces here, there will be accelerations. Accelerated charged particles emit electromagnetic waves, electromagnetic radiation. And electromagnetic waves, they carry energy, they carry linear momentum, and they carry angular momentum. Okay, electromagnetic fields are just as real as this object, which has energy, has linear momentum, has angular momentum, whatever. Electromagnetic fields are just as real as material bodies. Okay, so even though Newton's third law fails for the particles, okay, it doesn't mean that angular momentum isn't conserved. Angular momentum is still conserved. It is still true that delta L total, which is now equal to the change in the angular momentum associated with the particles, so massive objects in motion, plus the change in the angular momentum associated with the electromagnetic field. Okay, so if the angular momentum of the particles changes by that, then the angular momentum of the field changes by that, so that the change in the total angular momentum of the particles plus the fields is 0. So angular momentum is strictly conserved. Okay, and so when we start talking about fields, of course, electromagnetic field force interactions, we have to include angular momentum of the field. But still, angular momentum is strictly a conserved quantity. Okay, so we're not going to consider cases like this in Phys 121. In Phys 121, we're going to assume that we have situations like this or like this, so that the sum of the internal torques is equal to 0. And so all we're left with is that the time rate of change of the system angular momentum is equal to the sum of the external torques. Okay, so let me erase the board over here. I'll be right back and I'll summarize that result. Okay, just to summarize, we're going to assume in Phys 121 that the sum of the internal torques that one part of a system exerts on another part of the system, the sum of torque 1, 2 plus torque 2, 1, a vector that way and a vector that way, that those vectors always add up to 0. Okay, so the sum of all the internal torques adds up to 0. Okay, and then we had that the time rate of change of the system angular momentum was the sum of the internal torques, which we're assuming is 0, plus the sum of the external torques. So we're just left with the time rate of change of the system angular momentum is the sum of the external torques. Okay, so that's important. Now, this is exactly analogous to the idea in not angular momentum, but in linear momentum, where we're dealing with forces. Here we assume that the sum of the internal forces add up to 0. They all add up. So F12 plus F21 is equal to 0. So the forces of interaction satisfy Newton's third law, action-reaction. Then if that's the case, then the time rate of change of the system linear momentum is equal to the sum of the external forces. Okay, so these are completely analogous results. So what this thing says is that, sure, you might have particles or objects inside your system that are exerting internal forces on each other, but those internal forces, they may transfer momentum from one particle to the other, but there will be an equal and opposite amount of momentum transferred from the second particle back to the first, so that there's no change. So that internal forces do not change in any way the linear momentum in that system. Okay? The only thing that can change the linear momentum in the system are forces from particles external to the system. Okay? And so when, say, the change in the linear momentum of the system is in that direction, then there must be a corresponding change in the linear momentum of the particles external to the system in that direction, so that the total change, or the change in the total linear momentum, is equal to 0. Same thing over here. Now, instead of having particles, colliding with each other like this and just exerting forces F12, F21, we have particles exerting torques on each other. Okay, so here's one part of the system, here's another part of the system, and this particle is, say, this part of the system is spinning like this. So this is number 1, this is number 2. So number 1 is exerting a clockwise torque, so a downwards directed torque on object number 2, and that's going to increase its angular momentum in that direction. It's going to cause it to spin up. And so there's angular momentum in the downwards direction being transferred to object number 2. But at the same time, if there's a twisting force like this, a frictional torque like this, then object number 2 will exert a counterclockwise or upwards directed torque on object number 1, and that will transfer momentum to object number 1 in that direction. The original momentum of object number 1 was downwards. The momentum being transferred to it is this direction, so it's reducing the downwards angular momentum, and this object is slowing down. Its spin rate is slowing down. The top object's spin rate is slowing down. The bottom object's spin rate is speeding up in such a way that, so there's angular momentum being transferred between these parts of the system in such a way that there's no change to the total angular momentum in that system. Okay? The only thing that can change the angular momentum of a system are not internal torques, but external torques. Torques is exerted by particles outside of the system. Okay? So that's a very important general statement. So there's a special case of this case. There's a special case of this this general result here, and that's when we have an isolated system. Okay, so basically we just take this external particle and just remove it, and all we have left is this and this is isolated. Okay, and so the sum of the external torques is equal to 0, so the system angular momentum can't change. So, simple example of an isolated system, which is a very common example in Phys 121. We're going to say, okay, well, suppose that the sum of the external torques is equal to 0, either because there is nothing external to our system, or there are particles, but there's a torque that way and a torque that way, and they add up to 0. Okay, so if the sum of the external torques is equal to 0, then that tells us that the system angular momentum, the time derivative is 0, which means that the system angular momentum is equal to a constant. Or in other words, this is the same thing as saying the system angular momentum does not change. So delta system angular momentum is equal to 0. So the system angular momentum to begin with, whatever that was, no matter how they interact, exerting torques on each other and so on, the system angular momentum is the same initially as it is finally. Okay? So, so basically it's this case over here, delta L total equals 0 for an isolated system is equal to delta L system plus delta L external. But there's no external particles. Okay, and so that just disappears. And so delta L system is equal to 0, well, because it's isolated. Okay? So, so a super simple example of this is, say, Jupiter and the Sun orbiting around their common center of mass. Okay, so the center of mass of, say, the Jupiter-Sun system is, say, right at that point. And we will choose the point about which we are evaluating torques and angular momentum to be this point over here. So our origin here, our O point, will be equal to the center of mass of the Earth-Jupiter, of the Sun-Jupiter system. Okay, and so these two objects, they orbit on they orbit about their common center of mass. So this is, let's say, the Sun, and then over here is, let's say, Jupiter. This is the Sun, and this is Jupiter. Okay, and they orbit around their common center of mass. So the Sun will orbit in a smaller circle. Let's suppose they're circular orbits instead of elliptical, just easier to draw. And then Jupiter will always be located opposite that center of mass point on its own circular orbit. Okay, so they go like this. Okay, so later on Jupiter is over here and the Sun is over there. Later on Jupiter's over here and the Sun is over there, and so on. Okay, and so we can take this as, say, particle number 1, object number 1. This is Jupiter. It's got some momentum, say, p1 at this instant of time, and the Sun has momentum p2. I think this would be object number 2, p2, like that. And at this instant of time, we're going to be calculating angular momenta. Well, about what point? About that point. Okay, and so we need to identify, well, where is object number 1, Jupiter? Well, it's located over there. That's its position vector, r1. Where is object number 2, the Sun? Well, relative to the point O, its position vector is r2. That guy. Okay? And so then the first thing to say is, because here the sum of the external forces is equal to 0. So we're just imagining that our universe consists of the Sun and Jupiter, and there are no other planets, there's no other stars or whatever, there's nothing else exerting any forces on this system. So the sum of the external forces is equal to 0. If that's the case, then we know that the system linear momentum can't change. So delta P, the linear momentum of the system, can't change. So whatever it is at this instant of time, so P1 plus P2 is the total linear momentum in our system of two particles, it will always be the same. Okay, and so the linear momentum in the system is equal to the linear momentum of Jupiter at this instant of time plus the linear momentum of the Sun at this instant of time, which we call particle number 2. Okay, so that's the linear momentum at this instant of time, but that linear momentum has to remain constant. Okay, now what we want is we want this center of mass point to not be moving. So we are in an inertial reference frame where this point O is not moving. Okay, and so we want the center of mass point to remain at rest. So we want that constant linear momentum of the system to be 0. So the momentum of Jupiter to the left here is equal to the momentum of the Sun to the right at this instant of time. And so at this instant of time, the total linear momentum of the system is 0, and it will always remain 0. So later on, Jupiter will be over here with a linear momentum that way, and the Sun will be over here with a linear momentum that way, and those will always add up to 0. Okay? So remember, another way to look at this is the sum of the external forces. Remember when we considered the idea of center of mass and all that kind of stuff, the sum of the external forces is mass times the acceleration of the center of mass point. If we want that center of mass point to not be accelerating, okay, so we set that equal to 0. Sum of the external forces is equal to 0, so the center of mass point will not accelerate, which means that the center of mass point will move with a constant velocity. Okay, so it tells us that the velocity of the center of mass point of our Sun-Jupiter system can be moving with a constant velocity in any direction. So that's equal to constant. And we will choose that constant to be 0. We'll just catch up. We'll get an inertial reference frame and catch up with it so that that point, O, the center of mass of our system, is at rest in our inertial reference frame. So the velocity of the center of mass is a constant, and we'll just set it equal to 0 by choice of inertial reference frame. Okay? So that's dealing with linear momentum, and then we deal with angular momentum. So we have, there are no forces coming from objects outside acting on our Sun-Jupiter system, and so there are no torques. Okay, and so the sum of the external torques is equal to 0. Okay, so the sum of the torques coming from objects external to the system is equal to 0, because in this case there are no objects external to the system. And so that tells us that that the time derivative of the system angular momentum is equal to 0, which means that the system angular momentum is constant. So what is that constant? Well, the system angular momentum at this particular instant of time, and it will have that value for all times, at this particular instant of time, it's going to be the position of Jupiter at this instant of time, vector cross product with the momentum of Jupiter at that instant of time. So angular momentum is r cross p. We're evaluating the angular momentum about that point O. So we go r1 cross p1 plus r2 cross p2. So the position of the Sun at that instant of time relative to that point, vector cross product with the momentum of the Sun at that instant of time. Now you can see that these objects, this R1, this P1, this R2, and this P2, these are constantly changing. Okay? Even if they're circular orbits, their magnitudes don't change, but their directions change. If they're elliptical orbits, not only are their directions changing, their magnitudes are changing as well. So these things are always changing. Individually, they're changing. However, by conservation of angular momentum, this particular sum is equal to a constant. This R1 cross P1 plus R2 cross P2 is constant. And what is it? Well, R1 cross P1, we just apply the right-hand rule, is a vector that's pointing up. Okay? So this is R1 cross P1 is a vector pointing up. And then R2 cross P2 is also a vector pointing up. Both of these objects have angular momentum about that point in the upwards direction. So like rotating that way, okay, counterclockwise from the top looking down. And so then this total is equal to the system angular momentum, and that system angular momentum always remains constant. Okay, so as these guys orbit around each other like this, they will always have the same constant system angular momentum. Okay, so angular momentum is a strictly conserved quantity. Okay, so if you have an isolated system like this, then with no momentum, angular momentum entering or leaving, then the total angular momentum of the system always remains the same, no matter what the interactions are. Okay, and if we have, say, suppose that the angular momentum of our system is changing. Suppose that there's an angular momentum, say a change in the angular momentum of the system in that direction, then there has to be a change in the angular momentum of the particles external to the system in that direction, so that the total angular momentum remains the same. And so there will be then a transfer of angular momentum to this system in that amount. So to transfer linear momentum, a force acting over time transfers linear momentum. In the same way, a torque acting over time transfers angular momentum. Okay, so a force acting over time So, force times time is equal to the change in the linear momentum of this object. A twisting force, a torque, acting over time will transfer angular momentum to that system. Okay? So it's all very similar to the case of linear momentum for systems. We have analogous results for angular momentum of the system. So now let's do a really nice, rich example which will illustrate all of this stuff. I'll erase the board and come back.